In this unit, we take a look at comparing and contrasting the Sn1 and Sn2 reaction mechanisms for nucleophilic substitution. So in order to get started with this, what we'll do is take a look at the chart that I have here on screen. You can also access this using Canvas under Files and Handouts. So here, what I've done is summarized the different features of the Sn1 reaction in the column on the left and the Sn2 reaction on the right. It's useful to get a handle on these features because recognizing these different characteristics of reactions will enable us to determine whether the reaction follows an Sn1 or an Sn2 reaction mechanism. So first off, thinking about the rate of the chemical reaction, the Sn1 reaction rate is dependent only on the concentration of the electrophile, that is the molecule that has the leaving group. In other words, you can change the concentration of the nucleophile all day, up, down, all around, and you're not going to change the overall rate of the reaction because the rate limiting step of the Sn1 reaction is that first step of the mechanism where the leaving group breaks away from the electrophile, and so therefore the reaction rate is dependent only on that step. So the rate determining step involves that breakage of the bond between the carbon and the leaving group, where I'm representing the carbon here as R, and the leaving group breaks away. And so there is no nucleophile at that step. That's absolutely the step that holds up everything, and therefore that's the step that determines the overall rate. On the other hand, with the Sn2 reaction mechanism, for contrast, if we're looking at the rate dependency of that on our different reactants, that particular reaction at the rate determining step, which happens to be the only step of this mechanism, the rate determining step involves taking the molecule that has the leaving group and having the nucleophile attack that as the leaving group. So it involves the nucleophile coming in, attacking, and when we say attack, what we mean is that the electrons from the nucleophile are coming over to form a bond to the carbon atom that's bonded to the leaving group as the leaving group goes ahead and breaks away like so. And what that's going to yield for us is our product, where we will have replaced in one step the leaving group with the nucleophile like so. So in the Sn2 reaction mechanism versus Sn1, if you're looking at a reaction and you're having a hard time deciding whether it's an Sn2 or Sn1 reaction, one thing that you could look at is the dependence of the rate of the reaction on the concentration of the nucleophile. If the rate is dependent on the concentration of the nucleophile, then you need to assign it as an Sn2 reaction. If the rate is not dependent upon the concentration of the nucleophile, assign it as an Sn1. And just as a reminder of some of the key terminology that we're talking about in this chapter, when we have a rate that is dependent on the concentration of only one of the reactants, we say that the rate determining step must be unimolecular, una meaning one. On the other hand, if the rate is dependent upon two molecules, we say that the rate determining step is bimolecular. It has to involve, at the slowest step of the mechanism, those two molecules, the nucleophile and the electrophile, coming together. So next up on our list here is that we can think about the stereochemistry of the reaction. So the stereochemistry of an Sn1 reaction, typically an Sn1 reaction we consider to be not stereoselective, meaning that if we start with an R chiral center that is reacting, say we have an R chiral center bonded to the leaving group, so I'll go ahead and put CLV, and then I'm just going to label this carbon as R. We're envisioning that that's a chiral center and that we can assign it as R. Then what's going to happen once we have our reaction take place where our nucleophile comes in and reacts with that and the leaving group leaves, is that we're going to end up with a mixture of stereoisomer products corresponding to the R and the S configuration at that chiral center. So we'd end up with a carbon that is both R as well as mixed with a carbon that is S. And that mixture is very often racemic. Racemic means an equal mixture of two enantiomers. So if this results in the formation of an enantiomeric mixture of enantiomers that's equal 50-50 would say it's a racemic mixture. And so we would describe this reaction as being not stereoselective. The reason it's not stereoselective is because the nucleophile in this reaction is attacking an achiral carbon. So an achiral carbon, specifically it's attacking the trigonal planar carbocation, and it can attack that carbocation that's flat from either the top face of the carbocation or the bottom face, thereby giving rise to the R and the S products of the reaction. On the other hand, if we go over to the right side with the Sn2 reaction, the Sn2 reaction is stereoselective. And the reason it's stereoselective is because it's a one-step mechanism, which we saw up here at the top, where the nucleophile comes in and attacks the electrophile at the same time the leaving group leaves. And that necessitates that the leaving group leaves from the side opposite where the nucleophile is coming in, because if the leaving group's trying to leave at the same time the nucleophile is entering, there's not going to be any room for that process to happen if it's all occurring from the same face of the molecule. So the nucleophile has to do a so-called backside attack, which we mean by that attacking the side opposite where the leaving group is leaving. So that's going to result in the Sn2 reaction being stereoselective as long as the carbon that has the leaving group is indeed a chiral center. And due to that backside attack, what's going to happen is that the chirality of the product at that chiral center is going to be inverted relative to the starting material. So in other words, if the carbon started off as an R chiral center, at the end of the reaction, it's going to have converted into an S chiral center. And we say that's stereoselective. Stereoselective is our general term that describes reactions that have a preference for the stereochemistry outcome. And here there is definitely a preference because we prefer to make the inverted stereochemistry rather than a random mixture of the two possible stereochemistries. So next up on the list of comparing and contrasting the Sn1 and the Sn2 reaction mechanisms is the issue of carbocations. So with the Sn1 reaction, the Sn1 reaction involves the formation of a carbocation at the very first step of the mechanism. Remember that was the step up here where the leaving group breaks away there. I've boxed it in yellow highlighting there. And that yielded a carbocation. As a result of the fact that a carbocation can form, there are some interesting tricks that an Sn1 reaction can do. Namely, the carbocation can, in some situations, rearrange. And you should be looking for that so-called 1-2 shift, meaning the migration of a hydrogen or a methyl group by one position in the following situation. Look for a rearrangement if the carbocation is not stabilized by resonance. If the carbocation is stabilized by resonance, resonance is the most important factor for stabilizing, more important than induction. And so therefore, you would not do a carbocation rearrangement if there is resonance to move that positive charge of the carbocation around. And you'll generally have resonance in situations where that carbocation is allylic. The second thing is carbocation rearrangements will occur only if that carbocation rearrangement, or the so-called 1-2 shift, will provide a more stable carbocation. So a more stable carbocation, typically what we're thinking of here is we're typically thinking of turning a secondary carbocation into a tertiary carbocation, because tertiary carbocations are more stable due to induction since they have more electron donating alkyl groups associated with them. So when we're doing a 1-2 shift or a so-called carbocation rearrangement, it absolutely has to be productive, meaning it can't go from one secondary carbocation to another. It needs to go from a secondary carbocation to a tertiary carbocation to make the molecule more stable. On the other hand, if we take a look at the right-hand side here for the Sn2 reaction, Sn2 reactions do not involve the formation of a carbocation due to the fact that it's just a one-step mechanism where the nucleophile comes in and attacks at the same time the leaving group leaves. Therefore, there can be absolutely no carbocation rearrangement. So if you are looking at a reaction and the observation you make is that there has been a hydrogen move from one spot in the molecule to another, or a methyl group move from one spot of the molecule to another, indicating there's a carbocation rearrangement, then you can automatically say that that has to be an Sn1 reaction mechanism because of the fact that you observed that the skeleton rearranged for the molecule in going from starting material to product. In other words, on the other hand, if there's no carbocation rearrangement, it's possible that you're dealing instead with an Sn2 reaction. So that's that. And then the fourth thing on our list here of comparing and contrasting the Sn1 and Sn2 reactions is that if we're thinking about what type of carbon atom is preferred in each reaction, meaning a primary, secondary, or tertiary carbon bonded to the leaving group, the Sn1 reaction is going to be most strongly favorable at a tertiary carbon that is bonded to the leaving group. And the reason that's the most favorable is, remember that first step of the reaction mechanism for Sn1 involves the leaving group up here breaking away from our carbon atom. And so that rate determining step is going to be the fastest if we can make the most stable intermediate as a result of that step. And we're going to be able to make the most stable intermediate by induction if we do that step at a tertiary carbon. And so that goes back to that business about a tertiary carbon, carbocation being more stable than secondary and more stable than primary. And when we say most stable, by the way, we mean lower energy. So a tertiary carbocation is lowest in energy or most stable due to the additional alkyl groups that are bonded there that donate electron density toward that carbocation by induction. So the Sn1 is going to prefer to occur at a tertiary carbon bonded to the leaving group because that's going to give the most stable intermediate resulting from the rate limiting step. On the other hand, at a primary carbon bonded to the leaving group, it's going to be very difficult, if not impossible, to get an Sn1 reaction going there because of the fact that the carbocation that would result by breaking away the leaving group would be really, really treacherously unstable. So don't do that. All right, coming over to the Sn2, all is not lost with the primary carbons because the primary carbons, while they're terrible at Sn1 reactions, are really excellent at Sn2 reactions. So Sn2 reactions are most favorable at the primary carbon. And the explanation for that is due to so-called stereochemistry. Primary carbons have the least congestion around that carbon that's bonded to the leaving group, and so they're going to be most easily accessible by the nucleophile. So primary carbons are favored because they are the least sterically hindered. And when you think of stereochemistry, think of atomic crowding. And so when we look at a primary carbon, generally what you should immediately be thinking is that it's going to undergo an Sn2 reaction mechanism rather than an Sn1 because of the fact that the carbon that's a primary carbon has the least steric hindrance, which means that when the nucleophile is coming in up here at the top to attack that carbon, it's going to run into the least blockades along the way. And the other reason why we should be thinking of Sn2 for a primary carbon that's bonded to the leaving group is because that primary carbon is going to be a terrible candidate for an Sn1 reaction because it cannot form a stable carbocation. So with these features in mind, let's do an example problem or two where you are asked to provide the mechanism for a particular reaction and predict the products of the reaction based on some information or clues related to the reaction. So when you're thinking about predicting the products of nucleophilic substitution reactions, what mechanism they undergo, you're going to be thinking about the features that you see here in this table as your clues to diagnose what's going to happen in the reaction. So let's take a look at an example problem here to illustrate that. Okay, so let's take a look at this particular problem where we're asked to provide the major organic product and a mechanism for the following reaction given the experimental observations we can make below about the rate of the reaction, its dependency on the nucleophile concentration and the electrophile concentration. So now would be a good time to hit the pause button, see whether you really have the jam going about the Sn1 and Sn2 reactions, see if you can come up with the right product and the mechanism for this reaction. Then once you've done that, go ahead and hit play again and we'll rock and roll from there. All right, so let's take a look at the organic product and the mechanism for the reaction. The clue here to lead us down the right mechanistic pathway here is that the rate of the reaction depends on both the concentration of the nucleophile and the concentration of the molecule that's bonded to the leaving group. So that's suggesting, since the rate is proportional to both of those factors, that we must be dealing with a bimolecular rate determining step. A rate determining step, a slow step of the mechanism that involves both the electrophile and the nucleophile. Therefore, this has to be an Sn2 reaction that's going on rather than an Sn1 reaction. So, all right, let's go ahead then with our Sn2 mechanism for this reaction now that we've established that it must be Sn2 rather than Sn1. And in order to draw the mechanism for this, we need to know what in the world we're dealing with when we talk about sodium azide. NaN3 is known as sodium azide. Sodium, of course, is our Na. Azide is the N3, and that's an N3 anion. So sodium azide, we'd expect an ionic bond between sodium, so Na+, and the azide, the N3, the most stable Lewis structure that we can draw for that molecule is like so. We're going to have both terminals of this with negative formal charges. So I'm going to go and plug those in. We could calculate that based on the fact that there's 2 sets of lone pair electrons and 2 covalent bonds there on each of those. And then our nitrogen atom in the middle, since it has 4 covalent bonds and no sets of lone pairs, will have a positive formal charge. So in order to get this problem right, we needed to be able to recognize where the nucleophilic atom or atoms are going to be in sodium azide. And the location of the nucleophilic atoms are going to be right here at this end and at this end. And since the molecule is symmetrical, it doesn't matter which one of those you use as the nucleophile. It could be one or the other. So what we're going to do then, since we established this as an Sn2, we have to have the nucleophile come in and attack at the same time the leaving group is leaving. So I'm going to go ahead and draw in my 2-bromobutane. I'm going to go ahead and put the lone pairs in, which is always a good idea when you're thinking about mechanisms in order to keep track of who's going where and what electrons we have available to work with. And now what we'll do is take one of the sets of lone pair electrons from our nitrogen anion, because it's going to be the anion that acts as the nucleophile. Bring that over. It's going to attack the electrophilic positively polarized carbon atom at the same time that that leaving group breaks away. That's the hallmark of the Sn2 reaction. Remember, that's a backside attack. So the nitrogen is coming in and attacking from the side opposite where the bromine leaves, and therefore we're going to end up with inversion of stereochemistry, which we can show by simply converting the wedge to a dash to show that the group that's come in is bonded to the side opposite where the leaving group has left. So we'll go ahead and write in that nitrogen that's bonded there. That nitrogen still has one set of lone pair electrons that we haven't done anything with. It has a double bond leading it to the next nitrogen, and a double bond leading that nitrogen on to the other terminal of the azide. That other terminal still has a negative formal charge. Our carbon in the middle there, positive formal charge. There would be multiple resonance structures you could draw for this azide molecule. You don't have to draw those as long as you show one of them. You're good to go. And the other product of this reaction, since we're trying to get everything in our mechanism to show where all the atoms are and the electrons are coming from and going to, would be our bromide anion is a product of that mechanism as well. So with this example problem, what we've illustrated is how we can use information from these observations and features about Sn1 and Sn2 reaction mechanisms in order to enable us to come up with reasonable mechanisms for reactions and to allow us to predict the specifics about the products that we are observing here. So we've predicted our reaction product, this azide substituted molecule, based on our understanding of nucleophilic substitution reactions and our recognition that this has to be an Sn2 reaction due to the observations we make about the rate. So you should be able to handle this type of question using any of the pieces of data that we've talked about up top here in the table to ascribe the Sn1 or Sn2 mechanism to a reaction and predict the products of that reaction, including the stereochemistry outcome. So with that, in the next segment, what we will do is some additional example problems looking at some different Sn1 and Sn2 reactions and sort of further teasing apart these different features to allow us to predict the products of reactions.